Welcome back. Today we're going to talk about parametric equations and motions. And to start with, a parametric curve is a set of two equations. So we're going to work in parametric mode on our calculators. And what you're going to notice is there's an x equals a function of t and y equals a function of t. And the thing that is important to remember about parametric equations, like if this ball is flying, right here, so you go. So the ball's flying, it has horizontal distance that it's covering. So it travels for 1, 2, 3, 4 seconds. It can cover X amount of ground, right? X number of feet. And so its linear distance that it covers is a function of time. But also, its vertical position, so how high it is off the ground. 1 foot off the ground, 2 feet off the ground, 3 feet off the ground, whatever, is also a function of time. So parametric doesn't account for it all at once. It accounts for it in two separate equations. On an interval I, which is written A is less than T is less than B, for example. And so in these examples here, for the given parameter interval, graph the parametric equations. Here's the parametric equation. So X is equal to t squared minus 2, y is equal to 3t. And all we're going to do is we're going to spend some time working on getting into the correct mode. So here are the keys. 1, parametric mode. And so you're going to hit mode button. And you're going to go to para, right? The second thing that we need to do is the y equals button. Okay, so the y equals button, we're going to put into x sub t, we're going to put in t squared minus 2, and y sub t is going to be equal to 3t. And then 3, we're going to use the window button. So the window button up top. We're going to put in our t min is equal to the left endpoint. And our t max is the right endpoint. Okay, so meaning, for example, -3 for A, right? And this one would be 1. And what you're going to see is that's going to spit you out a graph that's different based on these three intervals. Okay, so you can work on those modes, so get into the correct mode, and the window is really what changes. So the thing that we take away from this is when the interval changes, the window changes. Okay, the interval changes, so the window changes. All right, so what we're looking at, the section of the graph that we're looking at changes. So what can we do with this? Well, what's pretty cool is, if you've ever studied physics, like a ball goes up and then it comes down, and there's an equation that we can use to model that, right? And so when a ball goes up and down, it's a parabolic motion. So it's like -16t squared plus v sub 0 times t plus your initial position. It's a parametric, right? Or sorry, a parabola, parabolic motion. When we talk about parameters, what happens is we've got x and y as represented by two different ones. So when we eliminate the parameter, that means write as one equation. So that's going to be solve for t. And 2 substitute in. So if I've got x is equal to 1 minus 2t and y is equal to 2 minus t, here's what I can do. That means that 2t is equal to 1 minus x, right? So I just rearranged things. So I added 2t to this side and subtracted x. So when I divide by 2, t is equal to 1/2 times 1 minus x. And so I'm going to take that and I'm going to plug that in for t. So y is equal to 2 minus 1/2 times 1 minus x. 2 minus 1/2 plus 1/2 x is 1/2 x plus 3/2, because 2 minus 1/2 would be 1/2, which is 3/2. Well, what do you notice? This is a linear equation. Okay, so this object, for example, doesn't go according to parabolic motion. This is a linear equation, so this is eliminating the parameter. If I go to this next one, check out what happens. To eliminate the parameters, combine as one equation. And so I am going to use this one, and I'm going to say that t is equal to y over 3. Well, watch what happens. X is equal to t squared minus 2. So x is equal to y over 3 squared minus 2 is y squared over 9 minus 2. And then I'm going to say x plus 2 is equal to y squared over 9. And so 9 times x plus 2 is equal to y squared. Watch what happens. Y squared is equal to 9 times x plus 2. I can't put this into my calculator, but I can kind of get an idea if I solve for y again, right? I'm going to do y is equal to plus or minus 3 times the square root of x plus 2. So that would be the square root of 9 and the square root of x plus 2. Why do I need this plus and minus? Remember, this is called an implicitly defined function. Okay, so this implicitly defined function means it's going to have a top, it's going to have a bottom. This is going to be the plus equation, this is going to be the minus equation. Together, they make up the entire graph. Parametrics are cool because they take into account the fact that you can have everything. Okay, you don't have to have this implicitly defined function. So y1 would be equal to the positive square root. So positive 3 times the square root of x plus 2, and y2 would be the negative. Negative 3 times x square root of x plus 2. Okay. So what do we do with these? Now these are the tricky parts because we've got this cosine t and sine t. We're going to talk a lot about this in the next section. But what we do with something like this is we need to rewrite it as a single equation. And so what we're going to do is we are going to spend some time discussing what exactly this graph would look like. So this is actually going to be a circle, and so we're going to go on this principle. X squared plus y squared equal r squared. This is a circle equation, right? And if I have x is equal to 2 cosine t and y equals 2 sine t, this is going to be a circle of radius 2, which is centered at the origin, but it's going to end up being 2 cosine squared t, let me start at the beginning. 2 cosine t squared plus 2 sine t squared is equal to x squared plus y squared. Okay, so I squared both of them. Why am I doing this? Well, anytime you see that x is like a 2 cosine something, or sorry, something times cosine t, and y is something times sine t, that's a pretty good hint we're going to have a circle here. And so this is 4 cosine squared t plus 4 sine squared t. And so it's going to be equal to 4 times cosine squared t sine squared t. So therefore, x squared plus y squared is equal to 4, because this is 1. That's an identity of this is 1. It's a circle of radius 2 centered at the origin. Okay? All right, finding a parametrization of a line through the points A, -2, 3, and B, 3, 6. So here's how it works. Here's the equation. In vector notation, it's going to be equal to this. x1 comma y1. Got to delete here. x1 comma y1 plus, and this is going to be t times x2 minus x1 comma y2 minus y1. What happens here? So my initial point, or in this case we're going to turn it into a vector, plus t times the vector between the 2 points. Does that make sense? So, you know, if I've got this point here and I'm going to another point, to define this vector, it's going to be whatever this point is as a vector, because it would be from 0, right? Plus the difference in those two, which defines this vector. So the difference x2 minus x1, y2 minus y1 is this vector here. All right, so we're going to add that to our initial one, which would be the distance from 0, 0, so it's that point. So x comma y is equal to negative 2, 3. It's going to be 3, so 3 here, minus a negative 2, so 3 plus 2, comma 6 minus 3. Check that out. Let's do a little simplification. Negative 2, 3 plus t times 5, comma 3 is equal to, now we got to simplify. So this is going to be negative 2, 3 plus 5t comma 3t. So it's equal to negative 2 plus 5t comma 3 plus 3t. So that's how we define this. Okay, so there's our x and our y. So x is equal to negative 2 plus 5t, and y is equal to 3 plus 3t. Okay, so you can do these next two on your own if you want to pause and try that one. Okay. The graph of the parametric equations is given. Find the values of the parameter t. We're going to skip that one. I don't want you to worry about that one. All right, I want to talk about this next one though. So a distress flare is launched from a ship's deck 75 feet above the water with an initial vertical velocity of 76 feet per second. Graph the flare's height against time. Give the height of the flare above the water at each time and simulate the flare's motion for each length of time. We're going to do most of that, okay? And I'm gonna show you and tell you why we're not going to do the other parts, but let's look at this as a whole. So basically what they're saying is the flare flies for this amount of time. Give the height of the flare above the water at each time. Simulate the flare's motion for each length of time. So, meaning, if you've got a flare that goes up and they shoot it, to graph is to show where that flare goes, right? So we have to construct an equation, and we're going to spend some time figuring out what exactly is going on here. So here is our general equation. Negative 16t squared, which is time, plus velocity sub 0 times t, so initial velocity, plus its height, and its height is equal to y sub 0, so where it starts from. So when I construct this equation, I'm going to have negative 16t squared plus my initial velocity, which is 76 feet per second, 76t, and it starts out at 75 feet above sea level. So no matter what t is, it's subject to this equation, right? And so my x sub 1 is t, that's my time. And my y is equal to negative 16t plus 76t plus 75. Well, all we have to do is plug this in, okay? This should be squared. All we have to do is plug this in, because when we plug this in, it's going to give us exactly the height of this flare. And so if we're graphing the flare, the height of the flare, we're going to plug it into this equation here. This is a height equation. So I want you to think about this. We don't know what it is, but let's just say a parabolic motion is like this. Well, look at this for a second. The height is going to be y. Okay? And so the other variable in this rectangular equation, right, in this negative 16t equation, is my x, which is equal to my time. Because as time ticks on, 1 second, 2 seconds, 3 seconds, we're going to see what happens to this flare. Now, this is obviously an incorrect graph, but what I'm saying is that's why it's x sub 1 is time, because time is the variable that goes in, and y is represented by our height. That's the parabola. And so when we evaluate for 1 second, you should get 135 feet. At 2 seconds, it's 163 feet. At 4 seconds, it's 123 feet. And at 5 seconds, it's at 55 feet. Well, think about what that means. If I'm on a ship, here's my ship, little portholes, right? And I am this guy here, and I'm shooting that flare. It's above, 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 and then at 5 seconds, so I know that this height is 75 feet. At 5 seconds, it's down here at 55 feet. And so that means that somewhere between 4 and 5 seconds, it drops below the line of the deck. Okay, so just kind of think about what that means and what the significance of that is. So why didn't we simulate the flare's motion? Because we kind of did here. This is kind of the simulation, right? It goes up, and somewhere between 4 and 5 seconds, it comes down. Let's talk about baseball. I've got a guy here, and he hits a ball. Kind of looks like a sword. And my horizontal motion is my velocity, my initial velocity, times cosine of theta. That's not new. X is defined by the cosine of theta. And this is my velocity sub 0. And my y component is v sub 0 times the sine of theta. And so this is our general thought here. This is our general premise. Is Kevin hits a baseball 3 feet. So this is 3 feet, which means that above the ground, this is height sub 0, with an initial speed of 150 feet per second. So this is 150 at an angle of 18 degrees with the horizontal. Will the ball clear a 20-foot wall that's 400 feet away? So think about it like this. Here's Kevo. He hits a ball. Here's the wall. What do I need to figure out? Well, think about it like this. If he hits it at 18 degrees with my v sub 0 equal to 150 degrees, I've got to figure out, right, v cosine theta, v sine theta. I've got to figure out, this ball flies, how far does it fly? Okay, so the wall is 400 feet away. When it gets to 400 feet, how many seconds has it flown? Like, how long does it take to get there? If it takes 4 seconds to get there, at 4 seconds, what is its height? And so I actually have to define 2 equations here. X is equal to v sub 0 times the cosine of theta times the amount of time that it flies, right? So my horizontal position is 150 cosine 18. That's defining it. Well, how long does it fly like that? How many seconds? I don't care about 10 seconds. I don't care about 1 second. I care about how long does it take to get to the wall, because I need to know when it's at the wall, what is its horizontal position? And if its horizontal position is 8 feet or 7 feet or 6 feet or 25 feet, that's what I care about. So think about it like this. I've got 2 simultaneous things going on. My horizontal position, how far the ball has flown, is equal to 150 cosine 18 times t. This is 150 times the sine of 18 times t. Well, what do I know? I don't necessarily care about the ball when it's at its peak. I don't care about the ball when it leaves the bat. I care about where it's at 400 feet. So I'm going to say 400 feet is equal to 150 cosine of 18t. Why do I care about that? I care about that because I need to know how many seconds it's flown. Okay? And so I could solve this. And so according to my horizontal component, my time, if I do this, making sure my calculator's in degree mode, it's 2.804 seconds. What does that mean? That means at a launch angle of 18 degrees, going 150 feet per second, 150 feet per second, it's going to take 2.804 seconds to get to that wall. And so I've got this 2.804 seconds, but the problem is, check this out. This doesn't take into account gravity. And so that's my vertical component, but it doesn't take into account of gravity. So, got to get my pen here. The path of a thrown object equation is what we just talked about up there. Negative 16 t squared plus, now, what's my initial velocity? Well, I need to figure out how this all fits in, and I account for this gravity and everything, this vertical component here, by doing v sub 0 times the sine of theta times t plus my initial height. Okay? And so this is my y equation because it takes into account the fact that this is just a vertical component, not taking into account gravity. This takes into account gravity. So, negative 16 times 2.804 squared plus 150 times the sine of 18 times 2.804 plus my initial height is 3 feet. And what I get is that this is 7.13 feet. And so if my wall is 20 feet, it will not clear. Will not clear. So what do? Horizontal component, and we took into account our vertical component by taking into account the path of a thrown object equation right here. That's where it fits in. Okay, there's a couple ways to solve this problem, but that's one way, and that's a good way to think about it. All right, guys, thanks for watching, and we'll see you next time.